Very pleased to introduce next Beth Clarke, who is an astrophysicist turned software engineer working at Capgemini Engineering's High Integrity Software Expertise Centre. That's a mouthful. Her work involves testing bespoke safety-critical software that keeps people safe in their everyday lives. She joined Capgemini Engineering in 2019 and has worked on a range of projects producing software for the rail, scientific research and satellite communications sector. Her enthusiasm and expertise in her field led to a recognition as one of the top female engineers in the UK as a finalist in the IET, which is the Institute of Engineering Technology, I believe, their 2020 Young Woman Engineer of the Year Awards, and being recognised as a rising star of women in technology by Computer Weekly in 2021. The first physicist I've met in an awful long time in software, I have to say. Beth's going to talk about testing high integrity software, methods and importance. Take it away, Beth.
Thank you very much, Paul. So as Paul said, I'm Beth and I am a test lead and test engineer working at Capgemini Engineering. But I'm also a scout. So I have been involved in the Scouts for just over 6 years. And I promise there is a point to me telling this story. I'd love to know if anybody who's listening in today has ever been a scout or a guide or had family in either movement. But the reason I bring this up is because I think that all scouts will make fantastic software testers. We're used to looking at requirements for the various badges that children complete, and we're great at user acceptance testing because we're always the ones who are there to try new badges and try out the requirements and identify any gaps and feedback. And we're also pretty good at A/B testing because we sometimes plan lots of activities for our programs, and on the night it might not work out and we have to readjust and retry something else and then see how that activity runs. And scouts just generally have an attitude of trying things out in the field. So they love to do things by trial and error, and they're really great at spotting problems early. That's really important in scouting to make sure that young people are getting the most value out of the activities. And all of this attitude is something that I also see in my life as a tester, you know, wanting to work out where the problems are early, wanting to try things out, give things a go, throw things at the wall and see what sticks. But why do I think that scouts have this attitude in the first place? Well, I think it ties into our motto of be prepared. So as a scout leader, I have a responsibility to make sure that myself, fellow adults, volunteers and young people that I all lead are safe. And so I have to prepare for every situation, as does everyone who's in the Scouts. We do risk assessments, we run trial camps, we update our skills training regularly and run our proposed programme through quality checkers to see if we're missing anything. And we have to check our plans against various badge requirements. So Scouts have to be prepared. If we aren't prepared for our weekly meetings, the kids may get bored and won't engage. And if we aren't prepared when we take young people away on a camp or on DV, as shown in the pictures on my slide, we risk potentially, you know, harming their health or risking their lives. We have to trust that our plans are correct and that we've thought of everything that can go wrong before we attempt anything. When you aren't prepared, you find out the hard way. So the photo on the left of my slide is actually when I went on a scout camp in the USA. There were 50,000 of us there. And we actually had a major sewage leak at 3 a.m, which caused a mass biohazard evacuation. So that photo on the left is us setting up emergency beds in the middle of the night. And why did that happen? Well, they should have tested the septic tanks a little bit better. But at least somebody had thought of this scenario and thought of a way to mitigate the risk in the event of a biohazard event. They tested out the plans. We were evacuated safely and calmly, all given somewhere to sleep, and everything moved on normally. My point here is I see a lot of overlap between my role as a scout and my role in testing high integrity software. And in both roles, I need to be prepared. I need to be able to trust the output of what I'm doing because my work mitigates some very substantial risks. And I also think that software is becoming more and more embedded in everyday systems. We're seeing the Internet of Things, we're seeing smart devices. And so I think that outside of just the high integrity and safety critical worlds, I think that everyone working in tech needs to be prepared for change, for new regulations, and new ways of developing technologies that all of our users can trust and rely upon for their safety. So I have got through a bit of agenda on the screen. So these are a series of questions that I hope to be able to answer in the next sort of 15 to 20 minutes. And then we'll leave you with a set of answers and actions at the end so that you can be prepared for the future of technology and the role it's going to play in keeping people safe. So on the slide currently are some traditional applications of high integrity or safety critical software. So air traffic control systems, monitoring where aircraft are over UK airspace and international airspace. Railway signalling systems, making sure that the right signal is showing that it can cope with scenarios such as landslides or wet tracks. Eurofighter typhoons, and the defense industry as a whole is a huge area for high integrity software. There's a lot of obvious risks when developing software for this industry because, you know, we're normally dealing with national security and things like that. So there are obvious safety critical applications there. And a diving computer for a rebreather. Again, very obvious safety critical applications, because if this doesn't work, then, you know, divers won't be able to breathe underwater and we potentially risk a loss of life. So these are some sectors that I've worked in before and my colleagues have worked in before, and obviously will continue to work in. These have always been a part of higher integrity software and will continue to be for the near future. But what I'm more excited about is this bottom row. So this bottom row talks about future applications of high integrity and safety critical software. So for example, autonomous systems is a huge up and coming area. We're seeing the rise of self-driving cars. We're seeing more prototypes be released in the future. And outside of autonomous systems in cars, you've also got smart factories and digital manufacturing, all things where the roles of people are being taken over by software-based systems. And it's really important that we need to make sure these systems work all the time. If a production line fails, that can lead to not only huge economic consequences, but depending on what's being manufactured, that can have a huge problem down the line. If we were manufacturing medical equipment, for example, and the software failed, then that is once again putting people's lives at risks. Systems reliant on AI. So this is an up and coming area in testing in general. How do we test AI systems? But we're seeing a lot of systems that involve machine learning algorithms. And so it's a case of, well, how do we actually make sure those algorithms are operating safely? How can we certify them as safe? What methods can we use to verify things like absences of runtime errors? And how do we predict what scenarios the AI is going to respond to and what it will do in each situation? Cryptography is another area. So there are lots of safety critical tools and libraries being developed at the moment. One I want to highlight is Spark SALT, or Spark NaCl, which is a new cryptographic verification tool, which is looking at, you know, making sure that information isn't messed with during transmission, that it's transferred safely, that can't be viewed by outside sources. And this is particularly important at the rise of quantum cryptography, because that's going to pose a whole other level of challenges in terms of safety, certification and verification. And lastly, with metaverse applications. So I know the metaverse is up and coming. Many people still see it as something that is only used for gaming or seen as a gimmick. But actually there are huge safety critical applications of the metaverse. For example, we've seen, if you've seen an advert for EE online, where they've had a barber shaving someone's face with a razor using a digital connection. That's kind of an early start of what the metaverse might look like. So it might be a way for surgeons to train for dangerous or risky or rare surgeries. And so we need to make sure that if they're in the metaverse practicing surgery, that it's as realistic to a real surgery as possible, but then also that the software is performing as it would in real life, because if it doesn't and somebody learns the wrong techniques when they apply that to a real patient, it could have devastating consequences. So all of these new and upcoming industries and sectors are going to require new certifications for safety critical development, and also a lot tighter regulation in order to ensure safety and, you know, that safety and security. So all of these applications, current and future, have a really common theme in that we are going to need to trust them. There's a need for trust in software, which is amplified in all of these examples in particular. But in general, the culture towards tech at the moment is we need to make sure we know exactly what's going on. We need to know it's going to be reliable, because tech is becoming a huge part of our everyday lives. So high integrity software can be really valuable as a methodology, because the methods and tools we use in development of these systems can provide strong assurance that bugs and defects haven't made it into our end products. And as we all know, we can never be 100% sure of anything in coding. We can never identify 100% of bugs with testing, but we do have the tools to get really close, which I will talk about in just a second. So as I mentioned, I've worked on some incredible projects just like this. And at Capgemini Engineering, we develop air traffic control software, defense software, and lots of other really cool bits of tech. I myself have worked on a railway signaling system, which was my first project when I started my career 3 years ago. And we do our best to keep people safe in a world where technology is at the heart of everything we do. And to illustrate the importance of safety in technology and the role technology is going to play in this, I've just put a couple of stats on the screen there. So we've had 1 billion passengers travel on aircraft controlled by a system that we developed, which is not a small number of people at all who are relying on our software to get them to their destination safely. In a separate project, we had 0.04 defects per 1,000 source lines of code in a product that was over 100,000 source lines of code long, and that was 1 year after delivery. So we're able to deliver this really high quality, really trustable and reliable software using methods from the high integrity software. The embedded software market is also growing, and as we move further into stages of automation and digitalization of our processes that were previously manual, software is going to start taking responsibility for even more aspects of our physical, financial safety and our security. But actually, you might be asking, well, what actually defines something as safe? What defines something as trustworthy? So safety critical projects tend to fall into a safety integrity level, or a SIL. The higher the SIL, the more risk is associated with that activity, as you can see in the matrix on the right-hand side there. So in general, SIL 4 projects, that highest level, would contain scenarios where the software takes over from people. And SIL 3 projects might be ones where the software monitors something, such as aircraft trajectories, and provides information to people, but where the people actually get the ultimate say in what action is taken. So an example of a SIL 4 system I've worked on is an emergency braking system on a train, where the train decides what parameters are safe and has the authority to put the brakes on without any input from the driver. So obviously needs to have that extra level of verification. This goes all the way down to SIL 1 and SIL 0, which are really quite low risk projects. And as you might guess, with the higher the SIL, the more rigorous the testing that's needed, and the lower the probability of failure needs to be. So you can see on the table on the left there that our probability of failures for SIL 4, that highest risk project, needs to be around 10 to the -5 in any given year, which is very, very small probabilities. Systems including software, hardware, or a mixture of both can be certified as adhering to one of these safety integrity levels. And that's kind of what we use to define as safe in my industry. Certification plays a key role in high integrity software development. And as I've said before, I believe emerging industries like AI and the metaverse will introduce stronger regulatory certification requirements related to safety, so that the certification requirements for high integrity software could actually be a basis for this going forward, and ensuring that these new technologies kind of don't run away from us. So what do we actually do to help meet these standards and produce safe software? So I'm just going to cover 2 of the various tools and processes that I've come across in my career. There are lots of others to choose from, and if you want to catch up with me after this talk to chat about them, I'd be really happy to. So verification is key. The role of testing in high integrity software cannot be understated. We need to be as close to 100% sure of absence of things that will make the code crash, so runtime errors. As mentioned before, in some cases, the probability of a crash or a failure needs to be as low as 10 to the -5. So formal methods are a really useful set of processes that we can use to achieve regulatory compliance in high integrity systems. So formal methods should be scalable. They should work on the smallest piece of software right up to things that are many hundreds of thousands, potentially millions of lines long. And it should be practical to achieve regulatory compliance. It should streamline that process. It should be automated and as simple to use as possible. So when we use formal methods, we model our source code formally. So our code is converted into a set of verification conditions. So these are like logical hypotheses that either need to be proved true or false using a tool I will come onto in a second. These verification conditions represent what is known, and conclusions representing what must be demonstrated in order for something to say, yes, this definitely has, for example, no runtime errors in them. So these types of conclusions that can be represented. So like I said, checks that runtime errors won't be raised, and also that checks that contracts are made, so that the relevant types of outputs are permitted within certain ranges, for example. So with formal methods, there are a range of tools to apply these, and some of these tools have automatic theorem provers, so they use a lot of discrete mathematics under the hood, and they're able to discharge or prove usually greater than 98% of the verification conditions that are generated for a piece of code. And what that essentially means then is only 2% of all the testing actually needs to be done manually. So this automatic discharging of verification conditions can take, as little as minutes for piece of software that may take days or weeks for testers to get through manually. And so those 2% that may not be able to be automatically proved is all the work that testers need to do. And so that makes much more efficient use of our time. It reduces the time to delivery and obviously reduces costs as well. Verification conditions can also help to ensure we've got maximum code coverage because it looks at logical paths through the code. And yeah, we're moving forward in an age of automation, so formal methods are a great way to implement that. And one of the tools we use for these formal methods is a tool called Spark. This is what we use primarily in my career so far. So Spark is a subset and a superset of the Ada programming language. So you can see that through the Venn diagram on the top there. So Spark itself is a programming language that is suitable for high assurance software development. And the tools within Spark perform a wide range of verification checks on the software source code, which are configurable to the context. And these include checks in the actual structure of your code. So Spark also leads developers towards a design approach that encourages kind of safety first thinking. These checks are performed statically. So Spark is a static analysis tool. And it forms one of the two key pillars of the verification of high integrity software, the other obviously being dynamic testing, which I'll come on to in a moment. And as I said before, automatic theorem provers embedded in Spark can discharge over 98% of verification conditions automatically. So whilst this verification may not be 100% automatic, whilst it's very close, it does still save significant engineering time. So the benefits of Spark include the proof of absence of runtime errors. It can check for information flow so that information from one variable or state doesn't leak into another or cause any side effects. It can produce partial or total correctness proofs, depending on the version of Spark you're using. You get the same program behavior with any conforming Ada compiler. And through all of this and everything I've mentioned before, this reduces the development costs of testing. So I've included a bit of a code snippet in there, which is written in Ada. And some of you may spot an error with it very quickly, but if you haven't, there is a huge error in this code which actually made it past a whole team of testers and was only picked up once the Spark static analysis tool was put in place. And the problem there is with the raw duration times 10 lines at the top. So the issue would actually be that raw duration times 10, if that happens to be a value that is larger than the integer range, then you get an overflow, which is obviously not very good in your code. So this just shows one of the benefits of Spark is that Spark enabled this bug to be spotted before it made it out into the wider world and obviously help keep people safe, but also, reduced our time and costs for the project too. So this covers the static analysis side of testing high integrity software. And as I said before, we've also got dynamic analysis and dynamic testing. We like to do both in the high integrity space just to add that extra level of verification. And dynamic testing is vital in safety critical projects. So this diagram I've got explains sort of the more traditional approach to testing that some projects may use. So the key points I want to highlight here are that our code coverage on the left side generally tends to come from the system under test or the software under test. We generally tend to look at code coverage through, the actual software we're testing instead of, a model or an oracle, which is on the right hand side there. Our test cases are derived from test conditions, and our test cases lead to a comparator. So we would run our test cases through the actual system itself and some sort of test oracle, compare the outputs and see if they're, correct with what we expect, and that produces our test results. So these are some changes for an approach called contester that we use in the high integrity world. The changes are highlighted in the red circle at the top. So firstly, a change I want to say is that test cases are derived directly from a specification. So this specification can either be written in plain English, or sometimes we like to use the Z language, which is a bit more formal as a mathematical language that can help us define requirements in a less ambiguous way. So the test cases are replaced by a controlled random input generator. So you can see that on the left, so test cases no longer appears in this diagram. We can derive them from Z, but they aren't test cases in sort of the traditional sense. There's no scripts involved for them. Usually it's not sort of a system level test. What we use those test cases to do is to define constraints on our inputs. So to define ranges or valid combinations of inputs, things like that. We then put those constraints into a controlled random input generator, and this then generates our input test data. So for those of you who maybe come from the hardware testing world, this might be something that's familiar to you, as that's where this approach has come from. But a benefit of using this random input generation is it allows repeatability of tests, because all you have to do is repeat the same constraints. But it also, whilst it allows repeatability from the constraints, it also provides that little bit of extra code coverage because of that random or pseudo-random element that allows us to pick different numbers within that range every time we run the test. Verification coverage is now on the right-hand side. So rather than coming directly from the software itself, the checks are now embedded within that oracle, that sort of reference model of the tests. Test conditions now influence the checks within the oracle rather than the oracle itself. So the oracle is just purely based on this from the specification, and as well some constraints from the random inputs, and it's those checks embedded in them, which in Python, for example, may look like if-else statements, and that's what gives us our coverage statistics, is how far through that test oracle we get. So in my experience, our oracle is normally written in Python, and the checks embedded within that, like I said, if-else statements. And this is for a method called referential testing. So we build the oracle using the same specification that's given to the developers building the system under test. And that system is normally written in a different language. Checks are embedded in the oracle rather than writing additional subsystem test scripts. And then we can run things back to back in the same way and compare our results. So the benefits of this approach as opposed to traditional testing are it's versatile. So you can use this at any level, right down from unit and component all the way up to system test. It provides greater assurance and quality because we have a high coverage of input and state spaces and corner cases through that random element. It's also very easy to drive a change in scenarios because all we have to do is change those constraints rather than going through and editing lots of test scripts. We have improved delivery and agility because it's reduced effort to determine the inputs required to satisfy test conditions, and it reduces the impact of specification changes. So if the requirements ever change, rather than having to go through and check all of your test cases individually, you just have to need to see if your constraints for your random inputs are still valid or not. This is also very compatible with lots of software standards in the high integrity world. And if you implement this alongside a diverse range of implementers, so a diverse set of testers who have got experience in the industry and other perspectives, that coupled with this approach reduces the possibility of a common failure. So I've talked a bit about the tools. I'm just going to quickly touch on the other side of the high integrity world, which is culture. So the tools and processes are one thing, and it's really great. And there are lots out there to choose from. I've just discussed 2 today, but there are plenty more out there. They assist with making our software reliable and trustworthy in a much shorter timescale and have obvious benefits towards certification. But these tools are nowhere near as useful if they aren't used with the right intentions and the right culture. They're just part of a wider ecosystem. There are, of course, many aspects to an organization's culture, but I just want to highlight 2 key principles that I think everyone working in tech, safety critical in particular, should live by or at least think about. So point 1, never compromise, quality over everything. Trust comes from quality. It comes from, delivered quality that is seen and understood by people. Going back to scouting again, the first line of our promise is that we will always do our best. Quality must be at the heart of everything we do and our top priority, even over things like deliverable time. And my second point is to value diversity of thought. diversity of thought is vital. Diversity of thought allows us to think about situations in new ways. People with different backgrounds may identify different gaps in the requirements based on their experience. So for example, autonomous vehicle safety rules, do they take into the account of different crash speeds on men's bodies versus women's bodies? Having a diverse group of people working on safety critical systems not only means that we identify potential issues faster, which makes development cost cheaper, it also gives us more assurance that our software is of a high quality to every user, not just one subset that's represented by the test team. So I'll just quickly go over a recap before I come into my actions. So my first question that I wanted to answer is, what role will technology play in the future of safety? And my answer is that I think technology lies in the very heart in the future of safety. And to prepare us for the future, we can learn lessons from the world of high integrity software, which I've hopefully explained what that is, which is it's reliable technology with safety at its heart. My third question was, which tools and processes are used to produce high integrity software? So I've talked about Spark and Contester for use of development and verification, but I've also talked about the importance of culture. You can't have all those tools without knowing why you should be using them or why it's important. So my last point that I had on my agenda was explaining how you and your organizations can be prepared. So my first action for you today is recognize the importance of technology in the future of safety. You are not exempt. Even if you don't work in the safety critical space, you are not exempt from the future of the software industry. Everyone in the tech industry is going to be impacted in some way by the trend of moving towards embedded, autonomous and digitized systems. Whether you're a software engineer, a safety engineer, a project manager, this will be something that you need to think about, and you should recognize this early. Number two, make use of the tools available to help you. Tools for the development of safety critical systems are readily available, and there's new ones popping up all the time. Some of you may have heard of a language called Rust, which is currently being developed to be safety certified through a tool called Ferrocene. Use these tools to your advantage. They'll reduce your development time, streamline your verification process, and ultimately just make your life much, much easier. And my final point and action for you today is look at your principles around software, system, and product development. Remember the importance of having the right ecosystem for developing safety-related software. This could be a big or small change for your mindset and the culture of your organization, but it can be worthwhile as a long-term investment for your future. If your principles are misaligned with your priorities and goals, this could cause huge issues for you. So thank you very much. That is the end of my presentation. Paul, I'm hoping we still have some time for questions.
Oh, yes, certainly have. Thanks ever so much, Beth, for that. You squeezed an awful lot in that short time.
Yeah, apologies. It's a whistle-stop tour. I could talk about it for hours.
Well, indeed, indeed. So, as always, there's a delay in getting questions out of people. I don't know what, so please use Slido to post questions for Beth. I'll have a conversation in the meantime, picking up stuff. So on and off, I've had a slight involvement to a bigger involvement in safety critical stuff, but not for quite a long time, 20 years maybe, honestly, that long. And my first reaction to what you said is nothing has changed. Now, I'm not saying progress hasn't been made, but the problems are the same. And it seems like the solutions, even though they're more sophisticated now, are also pretty similar. So safety integrity levels, static analysis and dynamic analysis, obviously that's moved on a hell of a lot since then. But we still have other problems that I'm not sure the tools solve. So I don't want to dwell on that because, you know, that's not a positive thing for you, perhaps. But anyway, let's see if we get onto it. But I'm also not sure who the audience are. So I don't know how many of them are working safety critical and who may not get it, you know, because obviously the first question would be, well, why isn't everyone doing this?
Well,
what do you think?
Yeah, I mean, that is a fantastic question. I think not everyone is doing this because it's a huge investment up front to work in this type of mindset, this type of methodology. It doesn't necessarily suit everything. So people working on app development, for example, may not have the strong regulatory compliance. And so an agile mindset might work better for them. And particularly with those low risk projects, like I talked about, those SIL 0, SIL 1s, where you might not need as thorough verification to get a safety certification. It may just be overkill, in other words, to go and adhere to these processes. But the other side of that is I think more and more areas of the tech space are going to need to start working like this in the future. So particularly anybody who works in embedded systems, this is going to be something for you if it hasn't already started happening for you. We've got so many new and exciting industries coming up at the moment, like I mentioned, the metaverse and quantum cryptography, that are starting to get away from us a little bit already. They're developing, people are taking them up quickly, everyone's very excited. But they are going to have implications on people's safety depending on the applications. They're not just going to stay as, the metaverse isn't going to just stay as something that's a game that people want to go and talk in VR. It's going to be a training tool for the medical industry. It's going to be a training tool for people who might want to work in factory settings, for example, and learn to use new tools. And it's going to be really important to make sure that we're adhering to various regulations that already exist, but also developing new regulations to make sure that we keep on developing software with safety at its heart, because ultimately software is a thing that's available to everybody now. It's in our phones, it's in our computers, it's in a lot of devices in people's homes now. And so it's actually going to be even more responsible for safety than it is at the moment.
Yeah, yeah. There was a question which got it appeared and then it disappeared. I don't know why. I'm not in control of it necessarily. But one of the questions was, how do you deal with specification risk? And by that, I would mean that we are still, as humans, not very good at writing down what we want when it comes to software. So even though you've got a software development program based on specifications, based on an ultimate requirement or specification, and you've built an automated Oracle, that Oracle is based on the same spec ultimately. So you're not going to discover requirements problems that way.
Yeah, absolutely.
What do you make of that?
So I've got two parts to my answer. So the first part is I think some of the issues with specification errors come from plain English or ambiguous language, things that can be interpreted differently by different people. So we tend to overcome that problem by using languages like Z, which are mathematically defined to not be ambiguous. And that has some of its own problems in that it's quite difficult to learn Z. Not everyone speaks it, so it's not necessarily an accessible tool. But if you want to minimize the ambiguity in your requirements, that can be a great way to go if you've got the resources to do it, or using some other formal specification. But my second point is one I brought up before about the importance of diversity of thought and diversity of teams, in that you need to make sure you've got a range of experience in your teams, particularly in the safety critical world. You know, you wouldn't want to be developing a piece of air traffic control software with a team where nobody's worked in air traffic control before. You'd want somebody in there who could look for common faults, who may be able to say, oh, actually, that requirement doesn't look right. You may even want a systems engineer to come and have a look at things. And so you're never going to 100% get rid of them, because like you said, we are humans, we are not perfect. But I think having a diverse team with a diverse set of experiences can hugely reduce the missing of those types of specification errors.
Yeah, I can't remember exactly when, but I bought a book. I heard of Z a long time ago, maybe in the late 80s. And it was called Z because it was meant to be the last language for specification, which I thought was a bit ambitious at the time. But you need to be an astrophysicist to understand Z. And that's the problem, is that most of our users don't. What you're doing is you're abstracting the problem higher and higher up the food chain, if you like. But in order to be an expert in specification, you then have to understand pretty formal logic.
Absolutely.
You know, and we don't have users like that very often.
No, we don't.
So we still
there's a lot of work being done in the specification space, because it is kind of one of the last frontiers to be conquered in the software development lifecycle in terms of testing. And I've heard of some tools that we're developing in-house that will sort of create automated specifications using like human readable syntax. So the same sort of logic as Z, in that it will be formally defined, but it will have you know, nice, easy to read syntax, kind of similar to Cucumber, I suppose, in that respect.
Oh, in principle, yeah. And when you say the last frontier, I think it's the only frontier.
Yeah.
So, and we haven't solved it in all these. Anyway, I don't want to dwell on that. The other thing, again, I'm being a bit of an awkward customer, I'm afraid. But
no, that's fine.
But also when when you say, well, we need people who've built this software before, the problem with that, I mean, the good thing is, yeah, they're familiar with the algorithms and the requirements and the end delivered product. They've seen it all before. The problem is they're probably going to build it exactly the same way they built the last one. And so they carry their assumptions into it. So when you say diversity, there's a real challenge of saying, well, do we use experienced people and live with less diversity? And that's kind of the downside. So again, it's a really difficult, these are all human problems, not
they're all human problems. And that's exactly why I brought up the point of culture in that wider ecosystem, because it really does impact everything we do. And on your point of having experienced teams, I think you can't just have people that have been doing this forever. You need to bring in new people, a fresh set of eyes, as well as to train them, you know, and bring up the next generation of software engineers and software testers. Like you said, it also gives that other perspective. It makes people question assumptions. So a mix is generally best.
Yeah, I mean, I think you have to sort of build in also a notion of, rather than just rely on the spec being perfect, which you never can, people think about things differently from the specifications perspective when they see some real software. So you still have this iterative feedback loop that people want to see working or maybe not working software to understand what they really, really want, because then when they see it, they think differently. They can visualize it in their own world, you know, kind of thing. So, you know, there's value in I wouldn't call it an agile approach in a safety critical world, but there definitely has to be these feedback loops at all levels, you know, to specifiers as well as people who are very highly technical, I suppose.
Yeah, absolutely.
I'm looking for more questions, but I'm thinking I'm not getting any.
That's all right.
So I have to say, just in passing, I'm not a physicist. I was never a physicist, but I kind of did an applied physics degree, and I stopped asking some years ago. But for years and years, I used to ask people in an audience, how many people did physics at university, and got no answer. And I found one person in Finland, and that was the only person I must have met, well, certainly hundreds, if not thousands of people. And it's very rare. I mean, what do you think physics brings to the party? Because physics relies on the laws of physics. You know, the real world obeys the laws of physics, whereas software obeys no laws, as far as I can tell. So we don't have that foundation. So how does that figure in your perspective?
Yeah, well, I'm interested to say you haven't met many physicists, because in my office alone, there are lots of physicists and astrophysicists as well in particular. Yeah, so I thought we were quite common. So that's interesting as a side point. But at least from my perspective, I think physicists entering at least software testing specifically, because when I was at university, you know, all physics students do labs. We all are trying and our best to make something work, and it's a huge, you know, test in resilience, and it's a way in testing, because, you know, a PhD student or a professor's written your instructions for your experiment, and then you give it to a bunch of first year undergraduates and see how many of them are able to understand it. And is that because there's a gap in their knowledge, or is it because you need to improve the specification, if you will? And so it kind of teaches that curious mindset of, you know, what will happen. And I think particularly with astrophysics, you have to have a curious brain to be an astrophysicist, because you're there asking questions about the origin of the universe and what's inside a black hole, and always wanting to find out more and find out the tiniest details of the inner workings of everything that kind of exists. And that's at least part of the mindset that I took into being a tester, is I want to understand everything. I want to give things a try. If it doesn't work, that's okay. I'm okay learning new things and, you know, failing sometimes. And I think that kind of willingness to explore is huge in software engineering in general, because we need people who want to innovate. We need people who have new ideas and different ways of thinking. And I think that's something that physics can bring to the table.
Cool. I have a view that maybe one of the ultimate ceilings that we'll hit in software is there are always people involved. And those people, it's a bit like, you know, the uncertainty principle. You get to a level of detail, if you like, where you can't know the, you know, simultaneously you can't know the position and momentum. I mean, let's not go into that game. Yeah. Because there's a fundamental uncertainty. And do you not think that having people involved in our software projects is that ultimate limitation that we've got?
Oh, that's a really interesting question, and a big question. I think obviously there are limitations. All humans have them. We make mistakes, like we've just talked about with specifications and things like that. But I don't know. I think if we didn't have people, we'd be more limited. I think if everything was automated and everything was done by, robots and software programs, that we'd lose an element of that user testing, that user acceptance testing, because at the end of the day, this software is being used by people. And so the best testers are people.
Yeah. I think that's true enough. I'm going to say thank you so much for the conversation. I mean, again, it's the sort of thing that could go on for some time, I have to say.
Yeah, absolutely.
So once more, Beth, thank you so much. And I hope to speak to you again soon.
Thank you very much, Paul. Thanks, everyone.